assume if the photoresist has a zero interfacial tension, nothing will stop the photoresist to make a very sharp 90-degree corner, even at a atomic scale resolution. So this will be very helpful in making these single electron-based, quantum-based, devices where you want to have everything at the nanoscale level, but still you don't want to have any rounding because of the final surface tension of the liquid involved. Okay. Second thing, which is the more, and that's the project what we have got from a drugs company. For example, all the drugs they come as emulsion. Okay, and all the emulsions need a stabilizer. So what you have a emulsion of a liquid A inside liquid B. Now the liquid A, if you have the 2 drops of the liquid A, it will mix together. Okay, so that's why you need to have a surfactant. But assume the liquid A and the liquid B has zero interfacial tension. So that means the drop of the liquid A will not coalesce with each other. So you can actually have a surfactant-free emulsion, which will be a blessing. Okay, so these are the 2 applications what we have proposed to utilize these zero interfacial tension environment liquids for following 2 applications. Okay, so this is the work we have just started. We have just got a proof of concept results and got a decent funding to pursue this work, and looks very positive. Last part, wrinkles. How much can I have? Okay, just stop me. Okay, so we see various kinds of pattern formation because of the instability. Okay, we see these sand dunes, which is because of the gradient in the air velocity because of the hilly structure of the sand. Okay, we see these clouds. People also call clouds as a fluid. Okay, so there is a very famous instability in the liquids called as a Rayleigh gliding instability. Rayleigh gliding instability is the reason why a liquid cylinder is not a stable configuration, because the liquid always wants to have a spherical curvature in all directions. Cylinder has curvature only in one direction, has no curvature in this direction. So that's why if you start the liquid cylinder, eventually it will break into the droplets. Okay? What I am talking is the elastic instability. That means the instability which appear or disappear based on the elastic applied force. Wrinkling. As you go old, the skin gets wrinkled. Okay, and that's what the cosmetic companies are doing. They are selling this anti-aging or anti-wrinkling cream. And we'll come to that. How does that work? So how do we make wrinkles? And that's answer to the question, Anjil. So what we do, we take a polymer, let's say PDMS, of certain thickness, certain length. We stretch it with a strain epsilon now. And after stretching, we expose it to, let's say, the plasma. So what we do, we oxidize the top surface of the polymer. We convert them into the oxide, silicate. Now, the elastic modulus of the film, which is the silicate, is much stronger than the elastic modulus of the substrate, which is still soft. So the bottom is the S stands for the substrate, F stands for the film. So S is still the soft polymer and F is the silicate oxidized. So EF is much larger than ES. Now you release this stretched film, which is now a multi-layer with a mismatch of the elastic modulus. So if you just take a single sheet and you compress it, what you will see a single bucket. You take a piece of paper, you compress it, it will just form one bucket. But if you take a 2-layer system with this condition and you solve the plane wave equation, what you will see, the solution comes like a plane wave. It will not be one bucket, but it will give you a k value. And corresponding to the k value, you will have a lambda value, that is a wavelength. Now this is still a soft system. So if you stretch them once again, it will get flat. And if you release them, it will again form the wrinkles. Like that. So these are the governing equations. After solving these beam equation with the 2-layer model, we get the wavelength, which depends on the EF and ES and the Poisson's ratio and the thickness of the film which we get after the oxidation. And similarly, what is the corresponding amplitude of these wrinkles? So this is the lambda and this is A. And these are the SEM images. We can create wrinkles all the way from, so we are using 2 techniques for the oxidation, oxygen plasma and also the ozone. So depending on the property of the HF and the EF, we get the wrinkle wavelength all the way from tens and hundreds of microns down to hundreds of nanometers. Based on your control parameter, and I'll count them, these are the AFM images of these wrinkles, and if you take a scan, fit the sign function, it looks quite such in nature.
It's very smooth.
See, we are not doing any topographic thing. We are taking a smooth polymer film, only oxidizing, and then releasing. We are not touching any of the top surface. So all the roughness of the original flat polymer film is present even in the reflex.
These are the empirical relations or
No, these are derived relations.